Welcome to this lecture 28 of the course on fundamentals of transport processes, and I was deriving for you the conservation equation in a spherical coordinate system. As I said, this conservation equation in a spherical coordinate system is important not just for spherical particles and so on, but because it gives us a deeper understanding of the diffusion phenomenon, and we will see that as we go along a little later. Okay. So, the spherical coordinate system, three coordinates in this coordinate system are r, theta and phi. R is the distance from the origin, and the unit vector ER is along the direction of increasing r. Theta is the angle made by the radius vector with respect to the z coordinate, and E theta is in the direction of increasing theta. As I told you, cos theta is given by z by r, where r is square root of x square plus y square plus z square. So, the maximum value that cos theta can have varies between -1 and +1. It is +1 if z is along, if the point is along the positive z axis, and -1 if it is along the negative z axis. So, cos theta varies from 1 to -1, which means that theta varies from 0 to pi. Theta is the azimuthal angle. Phi is the angle around the z axis, the angle that the projection of the radius vector onto the xy plane makes with the x axis. So, phi is the angle around the z axis, is the meridional angle. As you go all the way around the z axis and come back to the original location, phi increases by a factor of 2 pi. Therefore, phi varies between 0 and 2 pi. It is in this coordinate system that we started writing down our differential balance equation. When we write a shell balance, we have to write it for a differential volume which is bounded by surfaces of constant coordinate. In this particular case, the coordinates are r, theta and phi. Therefore, the balance equation has to be written for the surface at r minus delta r by 2 and r plus delta r by 2, at theta minus delta theta by 2 and theta plus delta theta by 2, and phi minus delta phi by 2 and phi plus delta phi by 2. And these surface areas do depend upon coordinates. Note that theta and phi are angles. They do not have dimensions of length, whereas in order to get a volume, you have to multiply 3 lengths in order to get a volume. And because this angle does not have dimensions of length, you have to actually take the actual length dimension along each of these directions. Okay. So, for the surface at r and r plus delta r, which I showed you in the previous lecture, this is the surface at r plus delta r by 2. You get it by multiplying 2 lengths. One is this length, which is obtained by increasing theta by a value delta theta. Okay. So, these angle subtended is delta theta, but the length is actually equal to r times delta theta. Okay. So, for the surface area r plus delta r by 2 is equal to this length r times delta theta times this length. Okay. Now, this length is obtained by varying the phi coordinate from phi minus delta phi by 2 to phi plus delta phi by 2. Okay. So, this is the length obtained by varying the phi coordinate. The radius vector in that case is r times sin theta. Okay, the radius vector is r times sin theta, the distance from the origin to this location along the xy plane. Angle subtended is delta phi, therefore, the length is r delta theta times r sin theta delta phi. Okay. Similarly, for the surfaces at phi plus delta phi by 2 and phi minus delta phi by 2, okay, which are the front and the back surfaces, one side here, okay, shown by the yellow, is delta r. The other one is r times delta theta, okay, at phi plus delta phi by 2 and phi minus delta phi by 2. Similarly, for the surface at theta minus delta theta by 2 and theta plus delta theta by 2, shown here by the orange, okay, surface on top and the surface below. For these surfaces, the surface area is delta r, which is the distance travelled. Okay. The surface is delta r, which is this distance, okay, times the distance travelled perpendicular to the phi direction, and that is going to be equal to r times sin theta times delta phi, that is this distance. So, the surface areas have to be constructed carefully. Okay, you have to take into account the actual length that is travelled, okay, in each of these coordinate directions. Once you have that, you just write the balance equations as usual. Change in mass in times delta t is equal to c at r theta phi t plus delta t minus c at r theta phi times t multiplied by the volume itself. Volume is delta r in the r direction. R times delta theta is the distance in the theta direction, and r sin theta delta phi is the distance in the phi direction. Similarly, the masses in and out at the surface at r and r plus delta r, surface at theta, theta plus delta theta, surface at phi and phi plus delta phi. All you need to do is multiply the respective fluxes by the surface area. Okay, so, you multiply the flux by the surface area to get the mass in and mass out due to diffusion. Similarly, for convection due to the mean velocity. Okay. Similarly, for convection due to the mean velocity, the mass in and the mass out, okay, is equal to, you just substitute c times u r for j r, c times u theta for j theta, and c times u phi for j phi. Note, j r, j theta and j phi are the fluxes along the r, theta and phi directions at a given location. Okay. However, the r, theta and phi directions are also changing in space. Okay. They vary from position to position. Okay. Therefore, one has to be careful while taking the components u r, u theta and u phi at a given location, because the unit vectors are changing with position. So, this gives us the final equation, and we divide throughout by the volume and time. Okay, we divide throughout by volume times time. Okay, divide throughout by volume times time to get a difference equation, okay, which basically relates the concentration difference between time t and t plus delta t to the difference in fluxes on the surfaces of this differential volume. It is not just the difference in fluxes. The surfaces of this differential volume, the surface area is also changing. It changes proportional to r, theta and phi. So, in addition to the change in fluxes, the surface area is also changing, and therefore, one has to have the surface area also coming in when one does this balance. Okay. The surface area is changing. It changes in the r as well as in the theta directions. Okay. The surface area is changing in both the r and the theta directions. Okay. Therefore, that has to come inside the derivative, because the surface area is not the same for the two surfaces. Okay. And once you take the limit delta r going to 0, delta theta going to 0, delta phi going to 0 and delta t going to 0, you get this equation for the concentration field. I can rewrite this equation a little bit. Okay. I take the convective terms to the left hand side as usual. I will get partial c by partial t plus square. is equal to so this is the differential equation for the concentration field. And now of course, I have to express the flux in terms of the concentration gradient using Fick's law for diffusion. Okay, I need to express the flux in terms of concentration gradient using Fick's law for diffusion. Okay. So, what is the flux? In the radial direction, Jr is equal to, let us first write it in differential form. Okay, let us first write it in differential form, minus d times delta c by delta r. Okay. That is in my Cartesian, in my spherical coordinate system, if I am at a location r and I go to a new location r plus delta r, okay, I take the value of the flux Jr at r plus delta r minus Jr at r and divided, I am sorry, by delta r. Okay, so from that difference, C at r plus delta r minus C at r divided by delta r, that is delta C by delta r. Okay. And if I take the limit of delta r going to 0, this is effectively minus d partial C by partial r. This is d times partial C by partial r. What is j theta? What is j theta? Okay. So, I start at some value theta, okay. Then I go to some other location theta plus delta theta, such that this angle is delta theta. Okay. So, I take C at theta plus delta theta, C at theta. This j theta is equal to minus d times C at theta plus delta theta minus C at theta divided by the distance travelled. Okay, the flux is equal to minus d times difference in concentration divided by distance. The distance that you travel in going from theta to theta plus delta theta is r times delta theta. Okay. This distance is equal to r times delta theta, that is the distance you travel in going from theta to theta plus delta theta is equal to r times delta theta. Okay. Therefore, this is equal to minus d partial C by partial theta, okay, minus d by r times partial C by partial theta. Okay. Similarly, if I were at a location phi, then I go to some other location delta phi away. Okay. So, I have C at phi plus delta phi. Okay. J phi is going to be equal to minus d times C at phi minus, I am sorry, C at plus delta phi minus C at phi by the distance travelled. What is this distance travelled? Okay. This distance travelled is equal to the angle delta phi times this radius. That radius is equal to r times sine theta. Okay. because r cos theta was equal to the z distance, square root of x square plus y square was equal to r times sin theta. Therefore, the distance travelled is r sin theta delta phi, okay, which if I take the limit of delta phi going to 0 is equal to minus d by r sin theta partial c by partial phi. Okay. So, note that the fluxes, they are not just, I cannot just write the flux as minus d times partial c by partial theta or minus d times partial c by partial phi. Flux has to have dimensions of a diffusion coefficient times concentration divided by distance. Theta and phi are angles, they are dimensionless. Therefore, one has to have, the flux has to have dimensions of the diffusion coefficient times a concentration difference divided by distance, and therefore, you get fluxes that are of this form, okay, in the theta and phi directions. Okay. So, it is important to note, because we have a coordinate system here in which the coordinates are do not necessarily have dimensions of length. Okay. The coordinates in this coordinate system do not have dimensions of length. Therefore, the expressions for the flux are a little more complicated. Okay. Now, if I insert these expressions into my original concentration equation, dC by dt plus 1 by r square d by dr r square c u r substitute the expressions for Jr, J theta and J phi into this, I will end up with a differential equation of the form dC by dt plus 1 by r square d by dr of r square c u r plus 1 by r sin theta. Minus So, this is the final differential equation that you will get if you substitute the expression for the flux into the concentration equation that I had just above. Okay. Physically, this equation can be written as we had done in Cartesian coordinate systems as dc by dt plus del dot uc is equal to d del square c plus s. Only thing is that the operators now are slightly different. Okay. So, this is the concentration equation in terms of the concentration field. If I write it in terms of the fluxes, I will get dc by dt plus del dot uc is equal to minus del dot j plus s, okay, where j is the flux vector. J vector is equal to minus d grad c as usual. Where the gradient operator is now defined as grad c, okay, is equal to ER times partial c by r partial r plus E theta by r partial c by partial theta plus E phi by r sin theta partial c by partial phi. This is the gradient operator. Okay. It is basically I can write, if I write j is equal to jr er plus j theta E theta plus j phi E phi. Okay. J vector is written as the sum of its components in the r theta and phi direction. So, that j is equal to jr er plus j theta E theta plus j phi E phi. Gradient operator is written as er times partial by partial r plus E theta by r partial by partial theta plus E phi by r sin theta partial by partial phi. Okay. Note these additional terms that come in here, because theta and phi do not have dimensions of length. Okay. The theta and phi do not have dimensions of length. Therefore, I get these additional terms here. That is the gradient operator, the gradient acting on a scalar. Okay. In this case, the gradient acts on a scalar. Okay. I have defined these terms in terms of a divergence operator acting on a vector. Okay. I have defined these terms in terms of a divergence operator acting on a vector. Okay. Therefore, the divergence operator acting on a vector del dot cu is equal to 1 by r square d by dr of r square c u r plus 1 by r sin theta d by d theta. So, this is the divergence operator in a spherical coordinate system. Previously, in a Cartesian coordinate system, our gradient was just equal to Ex d by dx plus Ey d by dy plus Ez d by dz. In this case, it is more complicated because the theta and phi coordinates do not have dimensions of length. Similarly, in the case of Cartesian coordinates, the divergence of c times u was simply defined as d by dx of c ux plus d by dy of c uy plus d by dz of c uz. In this case, you are getting more complicated forms, and I showed you that is because the surface area of surfaces of constant r is changing as r changes. Surface area of surfaces of constant theta also changes as theta changes. Okay. And because of that, you get more complicated forms. Okay. And finally, we had defined the Laplacian in a Cartesian coordinate system as 1 over r square d by dr of r square c u r plus 1 over r square in a Cartesian coordinate system as d square by c by dx square plus d square c by dy square plus d square c by dz square. So, in the Cartesian coordinate system, we had defined that simply in terms of the second derivatives with respect to the coordinates. As you can see here, if the right hand side is equal to d del square c, this is a more complicated form of the Laplacian in a spherical coordinate system. Okay. So, in the spherical coordinate system, I will define the Laplacian del square c is equal to 1 over r square d by dr of r square dc by dr plus 1 over r square sin theta. So, this is the Laplacian in a spherical coordinate system, once again a slightly more complicated form. Okay. And once again, as I said, the reason is because first of all the angles do not have dimensions of length, and secondly the surface areas are varying in curvilinear coordinate systems. Okay. The surface area vary with position in a curvilinear coordinate system. Okay. But once it is defined in this manner, the mass conservation equation in vector form is exactly of the same form, okay, for both Cartesian and spherical coordinate systems, okay, when it is written in terms of vectors. Okay. One doubt that naturally occurs when you write the gradient and divergence in this form is that the gradient of c as expressed here is just equal to E r times dc by dr plus E theta by r dc by d theta plus E phi by r sin theta dc by d phi. Okay. So, why is it that I get a more complicated form when I express the gradient, the divergence, which is basically the dot product of the gradient and a vector. Okay. This is basically just the dot product of a gradient operator and a vector. In that case, why do I get a more complicated form for the divergence? Similarly, del square is just del dot del. So, why is this not, why does this not appear to be just del dot del? Okay. I will briefly go through the reason here. Okay. I will not give you a detailed explanation, I will just give you briefly the reason why these assume more complicated forms. I define the gradient as E r d by dr plus E theta by r d by d theta plus E phi by r sin theta d by d phi. If I have to take the divergence of a vector, if I have to take the divergence of a vector, this is equal to E r d by dr plus E theta by r d by d theta plus E phi by r sin theta d by d phi of the vector. The vector is now in spherical coordinates. Okay, the vector is now in spherical coordinates. Therefore, I will have A r, the three components, A r, E r plus A theta, E theta plus A phi. E phi. So, if you are doing this just simplistically, the way that we did it in a Cartesian coordinate system, what you would say is that we will just take the derivatives of the components and take the dot product of the unit vectors. That is what we did in a Cartesian coordinate system. If you recall, in a Cartesian coordinate system, this was Ex d by dx plus Ey d by dy plus Ez d by dz of Ex plus Ay Ey plus Az Ez. This was in a Cartesian coordinate system. Okay. And the equivalent in the spherical coordinate system. In the Cartesian coordinate system, what we did was we just took the derivatives of the components and dotted the unit vectors to finally get dAx by dx plus dAy by dy plus dAz Az by dz. Okay, so, that was the simple solution in a Cartesian coordinate system. Note that strictly speaking, both the component and the unit vector are within the differentiation, are quantities that are being differentiated, and strictly speaking you should differentiate by chain rule. First take the derivative of the component times the unit vector, and then the component times the derivative of the unit vector. In the Cartesian coordinate system, we had the advantage that the unit vectors are independent of position. Unit vectors do not vary with location, and therefore, I was just able to take the unit vectors out of the derivative sign and take the derivatives only of the components. Okay. In the spherical coordinate system that we are considering here, the unit vectors do change with position. Okay. This is at one location. If I go to some other location, this is ER, this is E theta, and this is E phi. So, the unit vectors themselves are changing with position, okay, in the spherical coordinate system. That means that when I define del dot A is equal to ER d by dr plus dotted with AR ER plus A theta. Okay, when I define it in this fashion, okay, I have to take the derivatives here both with respect to the component as well as the unit vector, okay, and then take the dot product. And because the unit vectors are changing with position, I will get additional terms in the conservation equation due to the change of the unit vector with respect to position. Okay. And those additional terms in the equation for del dot A can effectively be shown to be equal to give these additional terms of this kind: 1 over r square d by dr of r square c u r plus 1 over r sin theta d by d theta of sin theta c u theta plus 1 over r sin theta d c d of c u phi by d phi. Okay. So, that is why the divergence has a form that is different from the gradient. Okay. Similarly, when I take the Laplacian, okay, del square is equal to del dot del, okay, which will be equal to ER d by dr plus E theta. Dotted with I have to take the derivatives of not just the components with respect to the r theta and phi, but also the unit vectors. And if you take the derivatives of the unit vectors, you will end up with 1 over r square d by dr of r square So, this is the Laplacian operator in a spherical coordinate system, okay. And you could do it in two ways. One way that I have just shown you by actually constructing a volume at surfaces of constant r minus delta r by 2 and r plus delta r by 2, theta minus delta theta by 2, theta plus delta theta by 2, and phi minus delta phi by 2 and phi plus delta phi by 2. Write down the balance equation for this differential volume, and from that you end up with an equation, the concentration equation right on top there, and identify the terms on the left hand side and the right hand side as del dot u c and d del square c. And once you do that, you get the definitions of gradient, divergence, and the Laplacian operator. The other way to do it is to actually use this expression for the divergence and the Laplacian and actually take the derivatives of the unit vectors with respect to r, theta and phi. That can be done. There is a well defined procedure for taking the derivatives of unit vectors with respect to coordinates, and when you do that you get exactly the same expression that I had got earlier by doing a shell balance. So, both of these procedures gives you exactly the same result. Whether you do it by a shell balance and then take the limit of delta r, delta theta, delta phi going to 0, you get a differential equation, identify the terms in that differential equation as the divergence and the Laplacian, or you take directly the derivatives of the unit vector. Both of these give you the same result. We will not do the second way by taking the derivatives of the unit vector, because we have not yet studied how to look at derivatives of vectors and tensors in vector calculus. But if you do it that way, you will get exactly the same result. So, that is the equation for mass conservation. The equation for energy conservation is quite easy to write. Okay. Substitute temperature for concentration, I should substitute the thermal diffusivity for the mass diffusivity. Plus S E by rho C P. So, that is the conservation equation for energy in a spherical coordinate system. So, this completes the derivation of mass and energy conservation equations in a spherical coordinate system. Momentum conservation equation we will deal with a little later. The reason is because, as I told you in the last lecture, momentum itself has three components, and for each of those components there can be variations in three different directions. So, it is better to look at momentum conservation equation after we have looked at after we have developed some basics in vector calculus. Okay. So, this is the mass and energy conservation equation in a spherical coordinate system. One can do a similar thing for a cylindrical coordinate system. One can do a similar thing in cylindrical coordinate system. I do not want to go into the details, I will just give you a brief overview of how one derives balance equation in a cylindrical coordinate system, and I will give you the final result. In a cylindrical coordinate system, the coordinates are r, theta and phi. Okay. I am sorry, the coordinates are r, theta and z. Theta, the meridional angle, is the same as phi, okay, for the spherical coordinate system. Okay. So, for any position, okay, the first coordinate is the distance from the xy plane, that is the z coordinate, which is the distance from the xy plane, okay, that is z. R is the distance from the origin of the projection of this onto the xy plane. Okay. So, r is equal to square root of x square plus y square. Okay. Z is the same as the z coordinate in a Cartesian coordinate system. R is equal to square root of x square plus y square. Theta is the angle made by this projection with respect to the xy plane. Okay. Theta is the angle made with respect to the xy plane. Okay. That means that cos theta is equal to x by square root of x square plus y square. Sin theta is equal to y by root of, and finally tan theta is equal to y by x. Therefore, the angle theta varies from 0 to 2 pi. R is the distance along the xy plane, so it always positive. So, therefore, 0 less than or equal to theta less than or equal to 2 pi, and r can vary from 0 to infinity. Okay. R is the distance, so the distance always has to be positive, and z is the distance along the z axis. Okay. So, this varies from minus infinity to plus infinity. We had solved using a cylindrical control volume for shell balances for a cylindrical coordinate system. Okay. If you want to derive in general a 3-dimensional conservation equation in cylindrical coordinates, okay, then the surfaces of the control volume have to be bounded by surfaces of constant r, surfaces of constant theta and surfaces of constant z in a cylindrical coordinate system. Okay. If you recall previously, when we did a cylindrical coordinate system, we had actually taken a cylindrical shell. Okay, for doing the shell balance. This cylindrical shell had height delta z in the z axis and the thickness was delta r. Okay, height delta z and thickness delta r. This is valid only for systems which have axisymmetry, that is, they are symmetric as you go around the z axis. Okay. In general, problems do not have axisymmetry. Okay. So, we have to take a cylindrical shell of bounded by surfaces of constant r at r minus delta r by 2 and r plus delta r by 2, surfaces of constant z at z minus delta z by 2 and z plus delta z by 2, and surfaces of constant theta at theta minus delta theta by 2 and theta plus delta theta by 2. Okay. That means that the differential volume that I consider has to be has to be of this form. Okay. This will be the differential volume, okay, such that the angle, okay, if I take the angle made by the projection, okay, onto the xy plane, this angle subtended is delta theta. Okay. So, I have two surfaces at constant r, okay, that is these ones. This is at r minus delta r by 2. There is another one on the other side at r plus delta r by 2. Two surfaces at constant z, the top and the bottom. This one is at z plus delta z by 2, and the bottom surface is at z minus delta z by 2. And then I have two surfaces at constant theta, theta minus delta theta by 2, and a surface at the back at theta plus delta theta by 2. And the surface areas for the surface at constant r is going to be equal to r delta theta times delta z, because r delta theta is this distance and delta z is the distance perpendicular. At constant z, at z and z plus delta z is going to be equal to delta r, which is this distance, times r delta theta. Okay. And at theta and theta plus delta theta by 2 is going to be equal to delta r times delta z. So, if I put all these together, put it into the conservation equation, divide by the volume, I will finally get an equation of the form partial c by partial t plus 1 by r d by dr of r c u r plus 1 by r d by d theta of c u theta plus d by dz of c u z is equal to minus plus the source term. Okay. If you recall, the terms that look like this are terms that we had already got when we did unidirectional transport problems. Okay. These terms we had already recovered when we did unidirectional transport problems. Since the derivatives in the z, since the z axis is identical to the z axis for a Cartesian coordinate system, the terms proportional to z are identical to these. Okay. These two terms are identical to what you would have in a Cartesian coordinate system. In addition, you have these two terms proportional to theta, which come about because of the transport through the surfaces at theta and theta plus delta theta. The expression for the flux will be equal to ER minus d into ER dc by dr plus E theta by r dc by d theta plus Ez. So, this is the gradient operator in a cylindrical coordinate system. That is the gradient operator, and the divergence del dot j can be written as 1 by r d by dr of r jr plus 1 over r partial j theta plus partial j z by partial z. Okay. If I substitute the expression for the flux into the conservation equation, then I get an equation of the form partial c by partial t plus So, that is the equation that I will get for the conservation equation. If I substitute Fick's law of diffusion, which is basically that J vector is equal to E r partial c by partial r plus E theta by r d c by d theta. I should put a minus d there. So, therefore, my Laplacian operator, if I write this equation as dc by dt plus u dot grad c is equal to d del square c plus s, and the Laplacian operator in cylindrical coordinates is equal to 1 over r d by dr of r. So, that will be my Laplacian operator in a cylindrical coordinate system, similar to the equations that we had got in a spherical coordinate system. Okay. And of course, the equation of motion for the equation for the temperature for energy transport problems is of exactly the same form, except I substitute T instead of C and the thermal diffusivity instead of the mass diffusivity. Okay. So, this completes the derivation of conservation equations in both spherical and cylindrical coordinates. These have more complicated forms. These are easily available. You can refer to standard textbooks for the formulas for the divergence, curl and gradient, as well as for the diffusion equation in these spherical and cylindrical coordinate systems. My objective here was to show you how these expressions actually come about. They come about exactly the same way that they come about in a Cartesian coordinate system. Choose a differential volume bounded by surfaces at constant coordinate. The change in mass within that differential volume is equal to the sum of mass in and mass out, and the masses coming in and out are the flux times the surface area. In cylindrical coordinate systems, the surface area changes as the coordinate changes, and if you do all of those correctly, you get the correct balance equations for both the cylindrical as well as the spherical coordinate system. No doubt these are more complicated than the equations that we had got, the simple equations that we had got for a Cartesian coordinate system. However, as we will see, they have some important physical interpretations, especially the spherical coordinate system has important physical interpretations which gives you much deeper understanding than the equations in a Cartesian coordinate system. So, this is the diffusion equation. Okay. I can write it simply as dc by dt plus divergence of u times c is equal to d del square c plus any sources or sinks. Okay. When we started this course, we talked about the relative magnitudes of convection and diffusion. Written this way, the left hand side is the time derivative, the variation with respect to time, plus the convective term. The right hand side is the diffusive term plus any sources or sinks that are there. Okay. So, therefore, if diffusion is large compared to convection, when the Peckley number is small compared to 1, you would expect d del square c plus any sources or sinks to be equal to 0. When convection is dominant, you would expect partial c by partial t plus del dot u c is equal to 0. We will now look at how to derive equations in these two limits. First, we look at the limit of low Peckley number where the diffusion is dominant, and we will be solving the equation d del square c is equal to 0 subject to boundary conditions. So, next lecture we will start our solution of the diffusion equation, and we will come back to the lecture on the convection on the high Peckley number limit a little later. Turns out we cannot just simply use this high Peckley number approximation in that case. We need to do something more complicated, and we will see that when we do boundary layer theory for Hyperactive number transport. So, we will start the diffusion equation in the next lecture. How to solve it? We will start with the spherical coordinate system. Solution is the procedure is the same. We have to implement a separation of variables. What does that give us and how can that be used for real problems? That will be started in the next lecture. So, we will see you then.